So sometimes the graph, the response, this is the response. You don't understand what is the response of the system. It's like when I pinch you, what do you do? Ow, that's a response. Yes or no? You need me to demo? No, right? Okay, here you go. So the first response goes like this. Okay. And then the second response goes like this. And then the third response goes like this. Now, so this, okay, so they saw a response like this. What is the common, so let's go back, so this is right. What is the common response of this tree graph? Yeah. Mathematically, yes, no time. Oh, what? Oh, damn, you short, right? It's a damn mechanical system. Damn, right? Right. So what's the response of this tree graph? What is the common feature that you see? All converge. So they are all what? Decaying. Right? Right? So they are all decaying. So after they know they decay, right? Right? After they observe they're decaying, they realize that y over t, or y as a function of time, must have a decaying function. By observation, they did not know. I repeat again, they did not know. You have to know how the history of. Then you appreciate the what? Then you appreciate the solution. If you don't know the history of how this thing is derived, you have no clue what is the solution. So they realize that there's a what? Decay. Okay. So on the feature over here, we can boldly say that over here, this is what we call over what? Over dam. Okay. Over here, we have critically damped. Now, critically damped situation is only mathematically, okay? Physically, not possible. Okay. And then the last one is what? Okay. How many of you are doing, all of you are doing math now? You all love math, right? It's fun, right? Are they all still using multiple choice to test you on math? It still are? Okay, unfortunately, it's a pain, okay, because there's too many of you, but embrace math. It's really, really important, okay? Another thing, math won't work is in the stock market. Are we clear? Okay. Stock market is all about gambling. Okay. The math don't work at all. Remember that. Okay. I tried. Nothing works. Right? So we have, it's like making the damn beer. Okay. So now we have this expression. Okay. So now we try to derive this expression. Okay, we try to relate this expression now. So we have to create solutions that must have a decaying function. For this case, right, it has to have a oscillation function also. So when it's under damped, we somehow have to squeeze in the what? oscillation function. Okay, why? Because we have what? We have cycles. Yes, ma'am. Yes. It's like a very thin line. Could you imagine a very thin line and my foot is on it? You perform either way. Okay, so mathematically possible, physically, like sometimes when you solve second order or when you solve second order polynomial equation, the time function can be negative. Is it possible? Like, no, right? It has to what? Move forward, yes or no? Right? So mathematically possible, it is only what? Impossible. Okay. Right. So let's now by embracing what I've told you already, right? So the equation that we try to solve, okay, which is equal to m d squared y over dt squared plus by c dy by dt plus by ky is equal to 0. Now we will solve this first. About 3 lectures later, we will then solve the what? The force vibration. Okay. So what we know for now, okay, this is known as the second order differential equation. Okay. Right. So if I were to move some, if I have to write the expression for this, sometimes we tend to have the expression written as my double dot plus by cy dot plus by ky is equal to 0. And as mechanical engineers are applying the rules of homogeneous, okay, we tend to have m double dot plus by c over my plus by k over my, the whole thing will be equal to 0. Okay. Now, in a second order differential equation, okay, we also have, I'm going to be a tree hugger. I'm going to split the page. We also have boundary condition. Okay. So the boundary condition, which is expressed when time is equal to 0, right? Y is equal to 0.15 meter, and y dot, which is equal to dy by dt, is equal to 0 meters per second. What does this mean? So if we were to go into the Excel spreadsheet, can you observe initial condition over here? Yes or no? Right. So if I were to change this time at 0, and I'll change it to 1, or not 1, 1 is a bad number, 5. What happened to the graph? The initial point where time is equal to 0, can you see it's gone up to 5? And then when I put it back to 1, goes back to 1, 0.15. So if I were to put this to minus 0.15, what does it mean? Initial condition. Remember, but you have to remember, in our Norman culture that we use, some of you say, Eugene, the freaking graph freak flip. No, what did I declare? I declare that coming down is what? Positive. Are we clear? Okay. Then the next thing that we do, okay, so by looking at the graph, right, you all can more or less understand how it works. Is that clear? Yes or no? Physically, what does it actually mean? Okay, let's do it. So physically, what does it mean? This is static equivalent. I pull down by what? 0.15, and I let go. The next expression that you see over there, is what? Is where time, is where velocity is equal to 0. So I have this at equivalent distance. I stretch it by 0.15. Velocity is equal to 0 means I'm going to let go. If velocity is positive, what does it mean? When I let go, I'm going to do this. I'm going to point down due to what? The function is a what? Velocity function. But the velocity function, if I 0.15, what does it mean? It's going to impulse. Okay, are we clear? If it's a sine wave, what does it mean? The velocity will flow going up and down, up and down. Okay. Okay. Now, I have not a clue if I change this to 1, what will happen? Oh, there you go. Okay. The graph, okay, the solution responds to the what? To the initial what? Condition. This is available on Avenue to Learn. If you are bored, okay, don't go to YouTube and watch the shorts. I like to watch shorts now. You all like to watch that? Yes or no? You don't like? Then you're in the bathroom for half an hour. Take your laptop, mess around with this. Are we clear? Okay, and have fun, I hope. Okay, so we put this back to 0. Right. So now coming back to here, right? So these are the boundary. Now you understand what the boundary condition physically mean. Okay, I like it when you all can physically understand what it means. So now, by observing the experimental system's response, right? Decaying function is required, right? So the decaying function, right, is equal to y is equal to e b as a function of time. It has to be a function of time because if you were to, pardon me, okay, I'm going to copy this so I don't need to go back and front. If not, I get headache, you get headache. Right? It has to be a function of time, right? So the decaying function is, this is the general trend of the graph. Okay, this is the graph all tends to decay down here. Okay, it tends to decay. That's the decaying function. So from here, we know that our mathematical expression or our solution has to be y is equal to e b exponential b power p. Now, I did not do this. Okay, this is derived very long time ago. But if you are going to, in future, derive mathematical expression, what do you need? You need the response. Are we clear? If you don't have response, you don't know what equations to use. Yes or no? Unless your name is like that crazy guy known as what? Einstein, Albert Einstein. He's psycho. He's beyond us. Okay. So we have to observe this from what? Experimentation. Okay. So that's why now you all know why we introduce a what? A decaying function. Okay. So you all can differentiate better than me. We have dy over dt. So this is equal to b e bt. Okay. And then if we differentiate again, we have this expression which is equal to b squared e bt. So this is also equal to y dot, and this is also equal to y double dot. Okay. So from here,